Types of reactions. We're going to classify each of these as an acid-base reaction or an oxidation-reduction reaction. Now, usually we call an oxidation-reduction reaction redox. So number one, this is an acid-base reaction. We know it's not a redox reaction because all of our species here have the same oxidation state. So sodium is a +1, oxygen is a -2, hydrogen is a +1, where chlorine is a -1. And over here, it's the same. Sodium is a +1, chlorine is a -1, hydrogen's a +1, and oxygen is a -2. So because the oxidation states do not change, that is an acid-base reaction. Number two, this is a single replacement reaction. Number one was a double replacement reaction, but number two is single displacement or replacement reaction. And this time we do have a redox reaction. This is oxidation reduction. So the oxidation state of sodium in its elemental state is 0, as is hydrogen. The elemental state of hydrogen, the oxidation state is 0. Here the hydrogen is 1, so it goes from a +1 to a 0. Here chlorine is a -1. Sodium is a +1. Chlorine is a -1. So it's the sodium that is being oxidized. Its oxidation state is increasing. And hydrogen is being reduced. Its oxidation state is decreasing. Here, again, magnesium is at a 0, so is chlorine. Elemental states are defined as having an oxidation state of 0. Magnesium chloride, magnesium is a +2, chlorine is a -1. So magnesium is being oxidized, chlorine is being reduced. This is a redox reaction. Number 4, we have magnesium oxide. Magnesium's a +2, oxygen's a -2, hydrogen's a +1, chlorine's a -1. Here, magnesium is a +2, chlorine -1, hydrogen's a +1, oxygen is a -2. So we don't have any change in oxidation state. This is an acid-base reaction. This is an acid. It starts with an H. And look, we're forming water. Here we have potassium phosphide. Potassium is a +1. This phosphorus is a -3. Oxygen in its elemental state is 0. Here potassium is a +1. Here oxygen is a -2. We have 8 of them. So this phosphorus must be a +7. So you see the phosphorus is being oxidized here, going from a -3 to a +7, and the oxygen is being reduced, going from a 0 to a -2. So this is a redox reaction. Here, let's see, we have a base. So I'm just going to write these out real quick, even though I think I already know what's going on. This is a -2. This is a +7. We've already figured that one out. This is a +1. This is a +7. This is a -2, +1, -2. So here we have an acid-base reaction. Acid-base reaction because here we have hydroxide. Hydroxide is our simple base, a strong base, and here we have an acid. And the products of an acid-base reaction are a salt and water, at least for the ones you will see in my class most of the time. Number 2, identify the atoms that are oxidized and reduced. The change in oxidation state for each in the oxidizing and reducing agents. Now here's where students can get confused with the semantics. So the reactant being oxidized is the reducing agent. It allows for the reduction to occur. The reactant that is reduced is the oxidizing agent. So here we have magnesium going from a 0 to a +2, so that is being oxidized. It's the magnesium that is being oxidized and therefore the reducing agent. The nickel here is going from a +2 to a 0, therefore the nickel in nickel chloride is reduced, and therefore it is the oxidizing agent. Here we have phosphorus, which is a +3 because each chlorine is a -1. This chlorine is a 0. Chlorine is a -1 here. Phosphorus is a +5. So the phosphorus is in, let's see, how do I write this? The phosphorus in PCl3 is oxidized. Therefore, the reducing agent, and the chlorine is reduced. Therefore, the oxidizing agent. Here we have oxygen in its elemental state, so it's a 0, and on both of these compounds, it's a -2. So the oxygen is reduced. That means something else is oxidized. So let's look. This hydrogen, we're going to assign hydrogen a +1. Hydrogen isn't changing, it must be the carbon. So the carbon is going to have +4, that should be a -2. And here, the carbon is going to be a -4. +4. That makes more sense. So the carbon in C2H4 is oxidized. Therefore, it is the reducing agent. So now let's complete these acid-base reactions. We have HCl, and we're going to react it with calcium hydroxide. That looks like a C. So when we're going to make an acid-base neutralization reaction, we're likely going to have water and our salt. In this case, it's the cation of the base and the anion of the acid. We need to make that compound make sense, make it electrically neutral. Now we can balance. So if I put a 2 here, then I have 2 chlorines and 1 calcium on both sides. Count my hydrogens. I need a 2 here. To be complete, we ought to have our phases. So these will all be aqueous. Well, this water can't be aqueous. Water is a liquid, and this is an aqueous substance unless it's a solid. So let's look at our solubility rules real quick. Soluble compounds include chlorine, exceptions to the halides. Nope, we don't have an exception there. So we do have an aqueous compound. Now we're going to take strontium hydroxide and add it to nitric acid. And we will form water and our salt. Now, if you don't know the charge on an element, always look for what you do know. You know hydroxide is a -1, and we have 2 of them. That means this element must be a +2. So to make this compound then, I need 2 nitrates. All nitrates are soluble, so that's going to be aqueous. Then we have our liquid, aqueous and aqueous. So now let's balance. If I put a 2 here so that I have 2 nitrates, I think I need a 2 here as well. And then we're balanced. Number 4, we're going to complete and balance these redox reactions. We're going to give the highest possible oxidation state for the oxidized atoms. Well, what does that mean? That means the metal is going to be the highest state possible if it can be more than 1. So my aluminum is going to make a +3, and when aluminum makes a +3, that means I need 3 fluorine ions, 3 fluorine anions in order to balance that charge. So aluminum fluoride would look like this. I'm going to need 3 of these, I'm going to need 2 of these, and 2 of these. The aluminum doing or completing a single replacement reaction here, bumping out this copper, the aluminum is going to make a Br3 aluminum bromide. And then the copper is going to be reduced to copper metal. So I'm going to need a 3 here and a 2 here in order to balance my bromine. Then I need a 2 for my aluminum and a 3 for my copper. Now for calcium and water, the products we're told are a strong base and a diatomic gas. Well, that strong base is calcium hydroxide. Diatomic gas is going to be hydrogen. Now I need to balance it. I'm probably going to need 2 of these, and I think we do balance. So that's 4. Just putting a 2 in front of water will balance that equation. To be thorough, we ought to have our phases, but we'll keep going. Number 5, complete and balance the equations for these acid-base neutralization reactions. So here we have magnesium hydroxide and hydrochloric acid. That's perchloric acid, not hydrochloric acid. So we're going to do a double replacement reaction. We have water, which is a liquid, and we have our salt. So we're going to have our magnesium and our 2 perchlorates. Now we need to balance. So I'm going to put a 2 here, and let's see, 2, 4, a 2 here. And then we have our balanced reaction. Here for this equation, again, I'm going to start with water, and that is a liquid, and then form my salt. So I have strontium sulfate. Now I'm going to check my sulfate ions are mostly soluble unless it has strontium. So that is a solid. Make sure I'm balanced. I need a 2 here, and then we're balanced. Number 6, write the molecular total ionic and net ionic equations. So the molecular equation is just what we've been writing so far. We do our double replacement reaction, and this is acetate. That's what this ion is. It's called acetate. And if you don't remember the charge, look, there's 1 hydrogen, and it's a neutral compound, so it must be a -1. So this is calcium acetate and water. Let's just double check here. We're going to need a 2 here, 2, 4, and a 2 here. And then we are balanced. Now the total ionic is what happens, and I'm going to leave the aqueous off of my aqueous substances, but the total ionic is what you draw when everything is aqueous. It breaks into ions. So everything on the reactant side is going to be an ion. And then everything on the product side doesn't necessarily break into an ion. So we have our calcium and our 2 acetates. And this time, water doesn't break into its ions. Water is going to stay just like it is. So that is our total ionic equation. Now to write our net ionic equation, what we're going to do is take our total and we're going to cancel out what's the same on both sides. There's a calcium on both sides, so I'm going to cancel it out. There are 2 acetates on both sides, so I'm going to cancel it out. So my net ionic equation, this time I am going to put the aqueous in, is going to be the ions on the reactant side that make up the liquid or solid on the product side. So now we're going to have phosphoric acid and calcium chloride. So the molecular equation is when we do our double replacement reaction here. So I'm going to make HCl and calcium phosphate. So I'm going to have a 3 here, PO4 2. I'm going to check my solubility rules for phosphates. So phosphates are usually insoluble. Therefore, that is going to be a solid. This is going to be aqueous. Now we do need to balance this reaction. So I'm going to put a 3 here and a 2 here. That gives me 6 hydrogens. So I'm going to need a 6 here. So that's my molecular equation. Now for the total ionic equation, I have a total of 6 hydrogens. I have 2 phosphates, 3 calciums, 6 chlorine. And that's going to react to form 6 hydrogen, 6 chlorine, and my calcium phosphate. Now, because my calcium phosphate is solid, it sticks together, even in the total ionic. So now I'm going to cross out what is like on both sides and form my net ionic equation. So I have 3 calcium ions, 2 phosphate ions, and that will react to form solid calcium phosphate.